just stand here. So those of you who are still feeling cold in this room, I'm feeling really hot. And one of the reasons is I'm wearing black color, which is not good for high temperatures, right? Right. So we ended up morning session with looking at silicon as a material detector. Now we are going to make a dark pixel out of it. Now, kinda going to assume a number of you know. Not really, we'll see. I'm not going to assume anything. Assuming anything is dangerous. So I gave you pictures of many painters. Just one more painting, just for fun. I knew you could not identify painters from Europe, but let's see if you can identify this gentleman. Somebody? Looks fairly. Stop Gemini for that. Stop Google search. That's not allowed. Google search was allowed for the Europeans. If you can't identify your own person, then he looks Indian, right? The topi and the thingy and the stick, everything is Indian. So who is he?
Raja Ravi Verma.
Not Lal Lajpat Rai.
Raja Ravi Verma.
He is Raja Ravi Verma. Then I was going to tell you, do you recognize these two paintings?
Saraswati.
Who told you Saraswati looks like that? That's Saraswati and Lakshmi, right?
Yes.
We all assume Saraswati to be like that, with a veena in her hand and a peacock on the side. We almost always assume Lakshmi to be like that as well. Not only that, we have these things in our mind of Kali and Lord Rama, with Hanuman sitting in front of them. Who told us they look like that? Raja Ravi Verma. We basically make copies of his painting and imagine gods to be like that. Remember, we didn't paint gods in past. By Indian tradition, we made sculptures. Now, sculptured gods don't look like this, do they? Next to Saraswati, you don't have a peacock sculpture like that. So it was Raja Ravi Verma's contribution which made us believe, and that's why, that's the sign of a great painter. You don't know the painting, but you all know the drawings. At least those of Hindu tradition would know, and even those not Hindu literature have seen this sometime or the other. Good, back to technology. So, imaging or camera making has been there for a long period of time, but it became very different in last century. And it was only about 100 years we went through 3 different technological reforms, 3 different ways of taking pictures. And all 3 were heavily successful. 2 of them are not even there in market anymore. Okay? So that was the first, the reel based, right? So they were kind of a chemical process. They're actually quite good cameras when it comes to dynamic range, bright and low light, and single shot, so global shutter. So when you switch on the mechanical shutter, it took the entire picture at one go. So it was not very bad camera, but the limitation was the number of cameras images you could take. Now in the 50s, we were trying to send the first space-going telescope up in the sky, and reel doesn't do very well with gamma radiations in the space. And that's when we started looking for a semiconductor-based detector. So the first to become market successful was this guy, charge-coupled devices. The way it operates is it kind of looks like banks of capacitors, or banks of PN junction one after another, each charged to a different voltage rate. And then light falls on it, electron hole pair gets generated, you store the electrons, and then after some time you move the electrons from one well to another. And very much your faces are saying, why is he going that fast? Everything else was slow. Moving fast because they ran for about 40 years. And they're also a dying technology now. They are not the technology used in your handhelds. The one which we use quite frequently in your handheld are pure CMOS based technology, the same technology in which we make all our processors and memory. Somebody is fighting next to us. So noise fighting, sir, or is it just entertainment? tea stall next to electronics department. That's an insult to electronics department. Do they give free tea to us? Should be banned. Well, you see, I don't drink tea, so I can afford to ban them. Wait till I become the director of this institute. The first thing to be. So, if you use spending most of today, tomorrow, and possibly half of day after tomorrow, spending on CMOS-based imaging technology. Now, the reason why we use CMOS is CMOS has generally got MOSFETs or transistors of some sort. But there's always a diode. There's always a PN junction, and a PN junction of any type will act as a diode. So it has diode, but it has very poor optical responses in past. But it has some promises, and the promises were, as the transistor becomes smaller, the diode also becomes smaller. So we can have more and more pixels in the same camera, which is very nice. As transistors become smaller, the power on which they operate, the voltage range goes down, which means we can have lower power operation. The cost also goes down because memory and processors, their cost is going down. So my camera cost will also go down. But the biggest promise was this. If we could make cameras in the same technology on which we make a processor, we can make processor and camera on the same chip. So that we can do image processing as we take the image. We can do a focal plane array or a human eye. That was a promise. We ended up completely not living up to that promise because our market said, forget about processing, just give me more megapixels. So we ended up taking the entire chip area just for pixels. Right, so some basic stuff about transistors. Can I just forget talking about transistors, diodes? Is everyone clear on their operation? So I'm getting the answer yes, which is a pendulum motion. No? Or no? Because you see, this is no in North India. So every time I come to India, I have to recalibrate my operations thinking. So the way I could differentiate between yes and no in South is if it's a undamped pendulum motion, it's yes. If it's a damped pendulum motion, dies immediately, then it's a no. Right? This is interesting because we do quite a lot of pendulum motions in our life. This is a pendulum motion, right? It's a nonlinear pendulum motion. Our heart is a nonlinear oscillators. Actually, both of them are examples of van der Waals oscillators. So I'm going to run through, assuming you guys know about transistors and diode, and that's the only thing I'm going to imagine. So don't worry, no more harder circuit complex than that. That's a CMOS inverter. You have an NMOS in the bottom, PMOS on top, and that's how transistors are made in a 2D process. So in order to make a transistor, you will have two N-type doping in P-type substrate, put a thin silicon oxide, put a metal contact or metal or polysilicon contact, and you have an NMOS type transistor. To make a PMOS type transistor, you do the same thing but exactly opposite to the N-type. Okay. Not of interest to us, but I just want to show what is of interest to us is this. Is a P-type substrate. In order to make the transistor, I put N-type dopant here. I'm already forming a PN junction. This is going to be sensitive to light. Light falls on it. Electron-hole pair will be generated. If I bias it properly, electrons will move one side, holes will move one side. I will get a current. So I will get a current with light falling on this and on the diode. Don't get me wrong, we can also make phototransistor, we can make photoconductors. But we will be looking simply at diodes. Now I've got some more diodes here. I have got here a diode, and I've got a deeper diode here. So already I'm getting three different types of diodes. An N-well P sub, an N plus P sub, and a P plus N-well. And if I have a triple layer technology, which I think the UMS process is, or which we are going to work, you will have a P bend here as well. And sometimes you have a deeper end. So any CMOS process gives you options of many different type of diodes. We're not looking at FinFET process, we're only looking at bulk process right now. Now, we designers really don't like choices. We're like men. Our trouser collection consists of black trouser, white trouser, and a blue trouser. Right guys? You know how hopeless we are. So there is a problem. We already have 3 different types of diodes and we need to choose one of these. Good. The other thing which we know how diode characteristics looks like. In the forward bias it goes exponential up, and the reverse bias is kind of fixed with bias voltage. Right? Now, the amount of light falling on the diode is going to, if we have standard light like this, what we have in this room, it doesn't have very high number of photons. It has high, but not high enough to lead to a very large current. So it's a small number of photons which are falling into. Not very small, not even one photon each. So if we are in the forward bias region, where the current is already very high, remember the current goes up exponentially. So operating the diode in forward bias means I need a big change in current to notice the current. But it's exponentially rising anyway. It's much better to be in the reverse bias region where the native current, the reverse bias current is small. So any small change in current, I'll be able to see. Essentially what happens is if that's my no light curve, light falls on it, that curve starts falling down. So I've got more current flowing here. Okay? So that can now act as a silicon detector. A PN junction will be. So the simplest camera you can think of is why don't we make an array of these diodes? Okay? The only thing which I need is I should be able to read from each diode separately because each pixel is a point. So I need some sort of a switch. What's the simplest switch I have? Any transistor is a switch. Right? If you apply a voltage lower than threshold voltage, it does not conduct current. Okay? So a simple NPN transistor or a PNP transistor can act as a switch. The simplest camera I can design will be something like this. I've got these diodes to capture light, and I've got a switch next to each diode. The switch either stops this light current flowing here or stays here or allows the current to flow. And then I can have, because I've got many rows, right? I'm trying to take picture of 2 dimensions. So I will have rows and I will have columns. So let's try to do kind of a row decoding. So I select first row first. Then the current output of each of these diodes start falling through these column lines. So rather than 2D array, now we can convert it into a 1D array. And then in the column line, I can have another multiplexer to somehow say, okay, first take this current. If I have a current, how can I convert it to a voltage? There are many ways. I can pass it to a resistor, I can pass it to a capacitor, I will get a voltage difference. So in one of these ways, I convert this into this is a voltage to current converter, I can convert current to voltage converter, I will get a voltage output. So first I select that row, then I select this row, I switch both of these 2 off. Now I have the current of these pixels and I have got it out. The simplest camera I want to make could be an array of diodes, each with a switch. Done. Let's go home. So anytime professor says this is a simple way, you know what's coming next. Why it doesn't work. Actually, it kind of works. It's not a bad camera as long as you want less number of pixels. Let's do some calculations to see when does it start causing problems. Some of the early cameras were arrays of diodes, nothing else. So I'm not going to force you to do this calculation, but hopefully I've done the calculation and you can visualize. I don't do much calculations, you will not see many numbers, but you can see that. So we agreed that energy of a photon is hc by lambda. So I made you do that in the morning. At this point you might say, if you're going to do this anyway, why did you make us do it? I think the answer to that, because I can, I'm a professor. So I took 600 nanometers, somewhere in between. That comes out to be around 2 electron volt. Silicon will give current in that. Now, so that is the energy of one photon. Now I need to know how many photons are falling on my detectors, because the number of photons will give me number of electron hole pair. And once I know my number of electrons, I can calculate my current. So if I now go by this relationship, which is how many number of incident photons are there. So energy of each photon is h nu. The total power of incident light is power. Divided these two, that gives me number of photons per second. And I know number of photons per second is going to be equal to number of electrons per second. So going by that, I do get a certain number of electrons per second, in this case 38,000 electrons per second for a typical power. Okay? And that, when I multiply with the amount of electron charge, gives me current. So each electron has 1.6 × 10 to the power minus 19 coulombs. That's the number of photons per second. So charge per unit time is current. So I get a current of about 6 femtoampere. That is a fairly small amount of current. It's not negligible, and that's the level of current which we are going to play with. We're never going to deal with more than nanoamperes of current. So all of you should be familiar with nano, pico, femto, atto. Now there lies the issue. So we're not only going to get the 6 femtoampere. That will depend. I mean, I'm taking for a typical light level. If my light level is low, I will get low number of current. If it is high, I will get high amount of current. Now let's ask, this is called a passive pixel sensor. There is no active circuitry here. It's just a diode and a switch. So let's now try to ask our question. Let's see bright light, because in a scene you will have different things, right? There will be some bright light. There's bright light here and there's low light. Let's just take 2 pixels. Bright light means high current, low current. So high current falling on this. Now this current moves through this path till this point. The path will have some resistance. I cannot make resistance less paths. Okay? It will also have certain capacities, because I now have a long wire running on top of a ground plane. That is a capacitor for me. It's a parasitic capacitor. Okay? So any wire is a capacitor. Now, of course, this is a wrong statement to make in first year bachelor lectures. To make capacitors, you need 2 parallel plates. What we often forget is ground can be a plate as well. So I have resistance of the wire, I have a capacitance of the wire. It immediately forms an RC circuit. RC circuit takes time to charge. Remember again, second year electrical engineering, you apply a voltage on RC circuit, it takes exponential charging time. And the charging time of an RC circuit depends on the amount of current you are giving it to charge. Right? Same with the discharging side. It has to discharge through a circuit. So a high current will charge this RC network very quickly. The low current will take a large amount of time to charge it. If this wire is long, if I have megapixels, to make a megapixel I need 1000 rows by 1000 columns. That becomes a megapixel. So if I have 1000 rows, which means this wire is 1000 times the size of each pixel. Now I've got a high capacitance to charge. So the small current will take a long amount to charge, which in turn means I need to wait till my line is charged before I can move to the next line. So the overall speed of the camera becomes very slow. Now remember when I talked about the first digital camera, I said it took 23 seconds to take a picture. Why was it taking 23 seconds? It was a passive pixel sensor. So all these numbers which we are going to talk about should have a scientific foundation. So a passive pixel sensor will kind of work, but will have different charging time in each one of them. There are a few more problems with it which we will see later on. Let's jump on to the sensor which actually makes sense. We'll start with a 3 transistor pixel circuitry and then go to a 4 transistor pixel circuitry which is in front. So our simple pixel, most pixels used in camera phones or mobile phones or for cameras general are based on this design. It starts with a photodiode which carries current. But we don't now want to read the current at all. Problem with current reading was this: the current has to charge all the column line. We don't want the current to charge column line. So what we would like to do is we would like to convert that current into voltage in the pixel itself. If I have a voltage, I could drive a high amount of current through the voltage to read it. So what we do is we do this. So we now have a reset transistor on top of it. So till now it looks very much like our passive pixel circuitry. But now I connect that node to a high voltage. That could be my VDD. Right now it is a VRST. That could be my power supply. Okay. If anyone doesn't understand, stop me then and there. If you don't understand, that's not going to be a crime. But when we're actually designing this in Cadence and that time you forget what I've taught you, that is going to be a crime. And then, what we do is what we ask is, this diode also has a parasitic capacitance. Agreed? Reverse bias PN junction has got a capacitance of its own. So let the photo current flowing through, let the photo charge being produced flow through this capacitance. It can't flow through the capacitance because capacitance blocks DC current. So what will it do? It will store the charge. All the negative charges will get stored there. Okay. And because it's a charge stored on a plate of a capacitor, the moment you allow it to move, it will form a current. Or it will become a voltage. So what we now, and after that, I have got a very simple source follower circuit, followed by another switch to select this particular pixel. Let's see this operation in a bit more detail and then it will become clear. So we start the operation by pushing this signal high. So I apply high voltage, this transistor becomes on. That voltage kinda comes on this node. I said the word kinda because there's always a VT drop, so it's not exactly the reset voltage, but it's a high voltage. So what I get is at the reset time, this node N1 becomes high. This is a select switch, it just selects to come on this one. This is a source follower circuit. I put the input at the gate of the transistor, the output is taken from source. What is the gain of a source follower circuit? You guys said you know about transistors. Give me a number. The worst it could be, you'll be wrong.
Can you come again?
What's the gain of a source follower circuit?
Ideally, it should be 1.
1, yes. Nobody asks you any more complex gain. The only time a question like this comes is when the gain is 1, 0 or infinity. The only 3 numbers in our electrical engineering, right? Electronics. You don't need it. All other numbers you have to calculate. So my trick is, and that's why I think I used to get jobs, was throw one of these, one of them have to be correct. And if you don't believe this, my job interview, I got one of the higher paid jobs in this campus. They asked me to draw the layout of a NAND gate. And I actually drew a NOR gate, but I drew it with confidence. To the level the guys got confused and got me a job. Much later, I visited Alliance Semiconductor and the guy who interviewed me met me there and says, "Oh, you confused me with the NAND gate layout." So give one of these 3 answers. What's the worst could happen? And I knew immediately after drawing it that And as soon as the second question started, I knew I had done a mistake. But I couldn't go back and say, by the way, could you stop? Let's go back to the previous question. Couldn't do that. So, that kind of has a gain of 1. So whatever voltage I see will appear here. Right? Input and gate. And this is just a switch. So whatever I see will appear here as well. Of course, I'm biasing it with a current which you don't see right now. The current bias can be bottom of the column. So let's start again. So I apply a high voltage here. This voltage becomes high. Then I switch this thing off. I remove this circuit completely from operation. Light is falling on the diode. What does light do? It produces electron-hole pairs. Here I've got a high voltage. Let's take I have 3.3 volt. 3.3 volt is going to attract. I've got electrons and holes which will get attracted to 3.3 volt. Holes or electrons? Electrons. Electrons are negative. They get attracted to the positive one. Right? So electrons will go towards 3.3 volt. And what do an electron do when it goes to 3.3 volt?
It creates a current in opposite direction. It creates a current in opposite direction.
It reduces. 3.3 volt is a high positive charge. The negative charge goes there, it reduces that amount. Right? So my voltage starts falling down. More electrons comes. I'm assuming it's the same level of current which is falling. My voltage starts falling down. So essentially I get a voltage falling down based on the amount of light which is falling. Slow light will slowly degrade it, high light will make it go low very soon. All the holes will be coming to ground. Okay. Now there is a level this voltage cannot go below. And if my chip has the lowest is 0, it's cannot going to go below 0. There is no way that it can go below 0, we'll see when it goes. But there is a level at which it saturates. Any higher light than this, it does not go 0 then. And this is what happened in some of the images which we took in the morning. Remember you took a picture of the bright light? And it just got a white shape. So not only was this thing saturating, neighboring to this was also giving enough light to go immediately to the lowest voltage possible. Okay? So that's the saturation. So what we allow them to do is we allow this for a finite integration time. We allow this current to, this voltage to form till a certain point of time which we call as integration time. And at that point we switch this voltage on, this switch on. Now this is connected to my output line. That's the thing which I read. I read the output here. And that is now going to be this voltage minus that current which has been flowing in it. Actually no. Why don't we do this analysis? So everyone has a pen and paper? Let's do this anyway. I don't have a blackboard to write. Tomorrow we'll get a whiteboard somewhere. So think of it this way. Replace this diode with a current source, which is my light induced current source. In parallel there is a capacitor. Okay? Now let's write what is going to be the equation of this voltage. So I will run through and backside. Then I have to remove this, okay? Actually, can we remove it for a minute and see what happens? Is it a manual or is it a... Oh, that's much better. Keep on doing it, let it go, let it go, let it go. Let it go.